Now I would like to discuss bonding in heteronuclear diatomic molecules. As the name implies, heteronuclear is when we have two different bonded atoms in our molecule. There are really two cases that we're going to discuss in the context of this chapter. The first case is when you have two different atoms, but they're close to each other in the periodic table. If they're close to each other in the periodic table, you can assume that their atomic orbitals have similar energies. So they're going to overlap in a similar way to homonuclear diatomics. So you treat them in a very similar way to homonuclears. For example, let's take the cyanide ion, Cn minus, and let's draw an MO diagram for it. So carbon and nitrogen are right next to each other in the periodic table. And that means that their atomic orbitals, carbon and nitrogen's atomic orbitals, are going to be really similar in energy. The three 2p orbitals on carbon are going to be very similar to the three 2p orbitals on nitrogen. Similarly, the lower energy 2s orbital on carbon is going to be similar in energy to the 2s orbital on the nitrogen. So if I have Cn minus, how many electrons do I have? Well, carbon has 4 valence electrons, nitrogen has 5 valence electrons, and the negative charge is going to contribute 1 valence electron. So 4 plus 5 plus 1 is 10 valence electrons that I have kind of available here. And I will fill out the atomic orbitals. I'm going to just put 1, 2, 3, 4 in carbon, and then I'll put 6 in nitrogen. 1, 2, 3, 4, 5. And I'm putting the extra 1 in nitrogen, 6. So going back to the table that shows the order of molecular orbitals for the various second row elements, so this is just a table from chapter 4 in your book. If I find carbon and nitrogen here on this table, I can see that the order of the orbitals goes like this. Sigma 2s, sigma star 2s, pi 2p, sigma 2p, pi star 2p, and sigma star 2p. That's true for both carbon and nitrogen. So I can just use that template for the order of my molecular orbitals in the cyanide anion. So that means that I'm going to put sigma 2s, followed by sigma star 2s, followed by pi 2p and sigma 2p. Then I have pi star 2p. And finally, sigma star 2p. So now I can take those 10 valence electrons and fill up the molecular orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I can see that this is a diamagnetic molecule, or ion in this case. And the bond order for this one is going to be, let's see, I have 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons minus only 2 anti-bonding electrons divided by 2. So 8 minus 2 is 6. 6 divided by 2 is 3. A bond order of 3 makes sense for cyanide because I know if I draw its Lewis structure that this is a triply bonded molecule. So a bond order of 3 corresponds to that triple bond in the cyanide ion. So that makes sense. The second case is when the atoms are very different, that is to say, very far apart from each other in the periodic table. For example, in the HF molecule, that's a diatomic molecule where hydrogen and fluorine are in totally different rows of the periodic table. So in that case, you have to compare the energy levels of their respective valence atomic orbitals. So this is something that you can look up. Hydrogen 1s has an energy, an absolute energy of negative 13.6 eV. eV is an electron volt, it's just a unit of energy. Fluorine's valence orbitals are 2s, and then there are the three degenerate 2p orbitals. The 2s orbital has an energy of minus 40.2 electron volts, and the three 2p orbitals have an energy of minus 18.6 electron volts. So now if I'm comparing these, I can see that the hydrogen 1s and the fluorine 2s are actually too far apart to overlap. But this value is similar to the value of 2p in fluorine. So that means that those two are more likely to be close enough to each other on the energy scale to overlap. So just to repeat that, the 2s orbital in fluorine, fluorine 2s, and hydrogen 1s are too far apart in energy to overlap. So they're too far apart to have any meaningful overlap. But the hydrogen 1s can potentially overlap with fluorine 2p because those two are fairly similar in energy, only about 5 electron volts apart. How could they possibly do that? Well, if you draw several things, there's really only one way that you could have productive overlap between hydrogen 1s and fluorine 2p. And that would be if you added the 1s orbital to the fluorine 2p x orbital, assuming that this horizontal axis is the x-axis. If you add those two orbitals together, you can get some really nice constructive interference and have some nice sigma bonding interaction along the bonding axis. Of course, if you add them together, you must also subtract one from the other to have a complete linear combination. And subtracting one from the other is equivalent to just reversing the phase. And if you do that, you would get destructive interference. So you're going to shrink that lobe in the middle, and you're going to end up with something that looks approximately like this, with an extra node between the nuclei. So that node means that this is a sigma star antibonding interaction. So we could draw a diagram, an MO diagram for the HF molecule with this in mind. The hydrogen 1s orbital is going to be a little bit higher in energy than the three 2p orbitals on fluorine. And then, of course, fluorine has this 2s orbital all the way down here that's kind of out of the realm of interaction. And of course, my y-axis here is energy. So nothing happens to my 2s orbital. I'm just going to draw 2s in the middle here because it's not going to interact in any meaningful way with the orbital on hydrogen. But I'm going to have some overlap between one of the 2p orbitals on fluorine with the 1s orbital on hydrogen, and that's going to give me that sigma bonding orbital. Conversely, I'm going to have the anti-bonding destabilized sigma star anti-bonding orbital. Two of the 2p orbitals are going to remain uninvolved. And actually, these orbitals, I can label them as non-bonding orbitals because they are not involved in the covalent bond between H and F. Similarly, this 2s orbital is going to be a non-bonding orbital. So now, hydrogen has one valence electron, and fluorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. So if I take those valence electrons, all 8 of them, and I put them in the MO diagram, it's going to look something like this. And this makes sense in the context of the molecule. If I draw the Lewis structure of HF, it looks like this. So I have a covalent bond, and the covalent bond arises from the 2 electrons that are shared in the bonding orbital. And then I have 3 lone pairs in non-bonding orbitals. So that's what these 6 electrons in the non-bonding orbitals correspond to. So we can see how you can have covalent bonds even in heteronuclear diatomics. You just need to find which orbitals are close enough in energy to overlap.